Saxon's Calculus, Review B, Section B, Geometry Review. So I went ahead and drew a lot of the shapes that we want to talk about in this review just because it takes a while to actually do them and I didn't want to waste the time on the video. So the first one here is we have parallel lines, and they should technically be marked with some arrows so that I know that they're parallel, and a line going through them called a transversal. And then what do we remember about the degrees? Well, A plus B forms a line, so that would equal 180. B is vertical with this one, which could also be labeled with a B. Vertical angles are the same. That's also what they're doing here. Vertical angles are the same. So A is vertical to A here. So here, the A plus B is a line, A plus B is a line, A plus B is a line, A plus B is a line. So they all equal 180, and then the subtractions would, of course, give you those same identical numbers. All right, so over here, I could label this one as my A being vertical. However, before I do that, we know that it's forming lines, as I've just said. So we have verticals, and then we have with transversals alternate interior angles and alternate exterior. So alternating means going on the other side of the transversal. So this B talking about on the other side, and exterior meaning on the outside of the parallels would be here is also a B, alternate exterior. Alternate exterior would put the A over here. Alternate interiors would be on the inside. So this B would alternate to the other side. Inside the parallels would be a B. And notice that still gives me my same AB combination forming a line. My vertical A here can alternate interior to here. Now this brings me to the last term, which is corresponding. So it's a combination of a vertical and an alternate. So, I'm sorry, I pointed the wrong thing. So vertical and alternate. This A matches this A. This A matches this A. They are combinations of alternate and of vertical. So anywhere I have the A's, it is the same. Anywhere I have the B's, it is the same degree. They're all forming combinations of lines, but we have the alternate interior, alternate exterior, and the corresponding. These were vertical angles. Now, this one reviews triangles. A plus B plus C will be 180 degrees. E plus A will be 180 degrees. It's forming a line. By subtraction, that tells me that E is the same as B plus C. That's a rule that we tend to forget. Yes, wanted to make sure I hadn't skipped any. Then I move on to this one, which is the reminder that in a circle, if you have an angle that is cutting an arc and it's coming from the center, these 2 degrees are the same. When you have an inscribed angle, it's not coming from the center, it's touching the side of the circle. The rule is that this degree is half the amount of the arc that it cuts. This one fits that same rule. It's inscribed angle. And when it goes through, it forms the diameter going through the center all the way across. And this would be 180 degrees. So if you follow the rule that it's half of that, then that means this has to be 90. So this corner has to be 90 degrees, no matter where it connects, as long as it's going through the diameter. And so that tells me that these are forming perpendiculars, and that it had to be 90, and that has to be 180. Yep, I gave you all of this. All right, now continuing on. When I have 2 secants, and that would be parts of lines cutting across a circle, not necessarily through the center, then the formula is the multiplication of the 2 pieces equals the multiplication of the other 2, because the chord has to be the same length in its multiplied form here. Now here, what we're saying is that Z and Z are vertical. They have to be the same. And if I need to find the Z, and I know these 2, and they're crossing inside the circle, I add the 2 arcs and take half, and that will give me the angle in the middle. If they cross, did they do that one? If they cross outside, yes. Here, when they're crossing outside the circle, not inside the circle, you are going to subtract the arcs y minus c and take half, and you will get the angle that is cut. All right, but coming back over to here, when I have tangent lines, now these were secants because they crossed through. This is tangent because it's touching the circle in one spot. Every time you have tangent lines that cross somewhere, the radius that touches the tangent line always forms 90 degrees. And we saw that we could cut this into two triangles, and we used that a lot in proofs with our circles last year. But you need to remember the rule that a radius touching a tangent always forms 90 degrees. And the length of these tangents will always be the same. So if they're connecting with the radiuses, these will be the same length. Then over here, I do have two secant lines. Again, this is just showing that they're extending, and out here they're connecting. So when this happens, we say that B times A will be the same length as D times C. They have to be the same, even though they're connecting at different spots. That's the rule. Here, same concept. A is multiplying with its entire line, which is another A, so that gives you A squared. That's going to match the outer D with the sum of the entire line, D plus C. This one we already looked at. And then these three are the same, which is why they didn't link it up here with this one. They linked it with these. And so here they're saying I have two tangents, and so it fits that formula. Minusing the arcs that are cut, taken in half, gives me the degree for the angle. If it's two secants that are crossing through, and you know what, I'm going to give you a more specific term here. When the secants, which are the lines cutting all the way through, this part are chords. So the parts that are just inside the circle we would call chords. All right, so it's still y minus c, take half to get that angle, whether they're tangents or whether they're secants, or a combination of tangent and secant. Same thing, y minus c, take half, gives you the angle. So that is all of the geometry review that they did on pages, well, technically it started bottom of 8, but the bulk of the information was on pages 9 and 10. Now, part C here talks about the distance between a point and a line. And distance should give you a key that we're using the distance formula, which we just reviewed, the square root of y2 minus y1 squared, I just said y's, plus x2 minus x1 squared, doesn't matter which order you put it in. That's your distance formula. Now, because this is calculus, they're moving us into wanting you to understand something different. And I'm going to pause long enough to redraw a graph. All right, so here is the picture that is going to begin to help us start to unravel a formula that I gave you one time in trig class as a supplemental video, because the former teacher preferred this one, which you didn't get to until the calculus book, but she put it in the trig book, and so I chose to explain it there. But this is a much more in-depth of why her formula worked. Okay, so what we're working with then is the distance between a point and a line. So distance, and then let me try to explain. This is the given equation for this line. AX plus BY plus a C equals 0. And we have a given point, which is our x1 and our y1. So what they're doing is that they're saying if we connect these, that's a certain distance. We don't know what that is, but the new point being created is the same on the x line over, it's x1, but the second value, the y value, is the y1 dropped down d places. So now you understand how so far what we're doing. And then we created a right triangle connecting. And so I labeled this one theta, and this distance was labeled B, and this distance is labeled negative A. Now, the slope of this line, and I could find it in the formula here, but what they're saying is that just using this triangle to find the slope is rise over run. The rise is negative A, the run is B. So that's the slope, negative A over B. That negative a over b is the same thing that I get if I do TOA, tangent, opposite over adjacent, negative a over b. It's all the same concept. So now you understand why they're graphing that graph. So then what they're going to do is they're going to take this coordinate point with the x1 and y sub 1 minus the d, and they're going to plug it into this line's equation and see what they get. So they now have a x sub 1 plus b with parenthesis y sub 1 minus d plus c equals 0. They then solve for the d in that equation that they got from here. And what they're getting is d equals a x sub 1 plus b y sub 1 plus c all over b. Now that's a part of the formula that's upcoming. So this is now the d of rearranging this graphed piece of information. Now I'm going to pause again and I'm going to add to this picture. Hang on. All right, so what I've added here is another triangle that is a right triangle connecting here to our original equation in which we had found D, and then I've labeled in some fishy Greek symbols, and so if it's labeled here, it's vertical to here, and it's also here in the triangle because this degree and this degree are the same, and the 90s are the same, then by default, the third piece has to be the same. The other thing that I added in was that Pythagorean theorem of b squared and this negative a squared would make this hypotenuse the square root of a squared plus b squared. So then if I find the sign of this symbol in this triangle, I get b over the square root of a squared plus b squared. If I find it in this triangle, I get it to be d over the capital D. And then if I substitute those things together, these have to be the same, and I plug in with this D into the formula, and I flip to page 12, I end up getting D equals, now there's one change in here that was not instinctively in the solution of these substitutions. It's the fact that this a x sub 1 plus b y sub 1 plus c needs to be in a positive format, so they put it in an absolute value so that you don't end up with any kind of negatives, but that's not part of my substitution because I didn't have that absolute value anywhere else. Over top of the square root of a squared plus b squared. And if you remember that formula from before, the distance was found by using this formula. So now they've proven to you with their slopes and their drawing of their so this is how they got to that. And I didn't go through that explanation before. I just proved to you how it worked. From the original formula, the number A is coming from here, and B and C and so on. So now that you have this again, they ask you in example 10 to find the distance between the point 1, 4 and the line y equals 2/3 x minus 5. And they're saying use this formula to do that. So I need to put my equation of my line in general form equaling 0 so that I can get it to this format that we need. So we're going to do 2/3 x minus the y minus 5 equals 0. And I move the y over. We got it equal to 0. But I also can't have it in fractions, so every part needs to multiply by 3. So this gives me 2x minus 3y minus 15 equals 0. And now you can do 2 as your A. Oh, distance equals absolute value of 2 times the x, which is 1, plus the negative 3 times the y, which is 4, plus the negative 15 absolute valued all over the square root of, and I know I've totally run out of room, a squared plus b squared. So my a was 2, 2 squares to 4, plus negative 3 squares to 9. So that's going to give me a square root of 13 on the bottom. And then 2 minus 12, negative 10, and another negative 15 is negative 25, and the absolute value of that makes 25. And even though I'm not supposed to leave answers with the square root of 13 in the bottom, usually when I'm doing this formula for distance, they will often stop it right there, but you can change that to 25 root 13 over 13, and it means the same thing. Again, I would prefer to go through my find the slope myself, flip and negate it, just do my formulas rather than this formula, but hey, if you like it, use it.